So lesson 5.3 is about solving the equations. So what we've done so far is we've learned what they look like, right? How that's related to zeros, turning points, all of that kind of stuff. Then because we knew that about the functions, we were able to make sketches of graphs, right? So now we could relate equations to graphs, especially in factored form based on yesterday's lesson, right? Do you guys remember that? That the factors were telling us locations of zeros, and then because we knew shape and end behavior, we could kind of fill in a sketch of a graph and what it looked like. Okay? So now what we want to do is actually solve the equation. When you're solving the equation, what are you finding? X, solution. Graphically, what are those? What's that? The zeros. Good. Okay, or x-intercepts of the graph. That's what you're finding when you solve. Okay? So just keep that in mind that, yeah, there's this algebra portion of it, but it can always help you with the graphical portion of it too, right? Because there's a connection between what you're finding there and what it looks like on the graph. So what are the ways we solved quadratics? Good. Factoring, completing the square, and quadratic formula. So none of those are going to go away. We're just going to kind of try to use them in a new scenario. Okay? So clearly we can't use the quadratic formula unless it's something of a quadratic form. So we're talking about when we can use that and when we can't use that. And completing the square, if we're trying to build a perfect square, again, it would depend on what the degree is of the function. But factoring, we saw yesterday, we could factor even things of a higher degree if we could factor out like a common factor or something we saw they had in common. So here, first I would get everything on the same side, and I'm going to write it in standard form. So we have our 3x to the fourth minus 12x cubed, and what I would do is just add 21x squared to both sides, so that it's set equal to 0. Because the first thing I'm going to try is I'm going to try to factor it. Because if I can factor it, it's a lot simpler for me to find the zeros. All right, so factoring. Somebody help me out. What can I do here? Alex. Okay, good. So I can take out a 3x squared, which would leave me with x squared minus 4x plus 7. Okay. All right, can we factor x squared minus 4x plus 7? No. Okay, so then going to solve this, we have two factors so far. This factor, and when we set that equal to 0, what solutions are we going to get for x? Okay, we're just going to get 0. So we're going to get one real solution. What is the multiplicity of that 0? Alex? Good. 2, because this factor is being squared. So if later on they ask me to like make a sketch or something like that, knowing that this was degree 4 and that this 0 had a multiplicity of 2 would help me know how the graph behaves at that 0. Okay? So anytime a factor, so here the thing that's being set equal to 0 is really like the x part of it, but there's not just one x here, it's x times x. So because there's two factors of x, both which could be set equal to 0, either way you're just getting 0 as the answer, but you could have gotten it twice because there are two of those factors. Therefore this is a 0, but its multiplicity is 2 because I could have achieved it twice based on this equation. Yes. Okay. All right, now this couldn't be factored. Does that mean that we can't solve it? What were our other options for solving? Quadratic formula, completing the square. Okay, so I heard more quadratic formula, so we'll go that route. This is a quadratic, okay, so we can use quadratic formula with this piece of it. So when I'm setting x squared minus 4x plus 7 equal to 0, it doesn't factor, so I'm going to try and solve this separate piece by using the quadratic formula. So I'm going to get 4 plus or minus negative 4 squared minus 4 times 1 times 7 all over 2 times 1. Okay. All right, so I'm going to work on simplifying. Specifically, it's the stuff in the radical that usually gives people a hard time. So there's a 2 in the denominator, a 4 here. And what number's in my radical? I basically have 16 minus 28, which gives me negative 12. Okay. Now, there are no real solutions then for that part of it, but they didn't restrict the directions to say only solve for the real solutions. So even though these aren't real, what I know is that tells me it's not going to tell me as much about the behavior of the graph as I'd want, because I don't really know where it turns around if I don't know the real zeros, right? Because those help me cross through the x-axis. So that means there's going to be part of this curve I don't know a lot about. But I can still list these as solutions written in the complex or imaginary form. So how do I simplify this and write it in the correct form using the imaginary numbers?
You separate the negative radical and then it becomes a negative 1 rad and negative 12, so that changes to I rad 12.
Good. So we're treating the radical of negative 1 is what's going to give us the I. Okay? And then the square root of 12 can be broken down, right, to be 2 rad 3. Is that okay? Okay, and then now, can I simplify this any further? Yes. Okay. Now, only if this can divide both of the terms that it is the denominator for do we continue, and in this case it can. So we get 2 plus or minus I rad 3. So we have 3 solutions, okay, to this quartic polynomial. 2 of the solutions are imaginary or complex. The other solution has a multiplicity of 2. So if you add those up in total, 2 complex solutions and a 0 that has a multiplicity of 2, you can see where you get your 4 total solutions, why it matches up with being a quartic. Okay? So we can solve the same ways we've solved before higher degree polynomials. Okay, so no new idea, just applying old ideas to a new situation. Any questions about solving it when it's higher degree? Then two.
Multiplicity is the number of, it's like the number of repeat solutions you have, and then degree is the number of the maximum number of solutions you can have.
The degree of the polynomial tells you the maximum number of solutions, and each solution has a multiplicity based on the power that is being used. Yes.
So like once x squared equals 0, or 3x squared equals 0,
yeah.
And then the multiplicity of 0 is 2.
Uh-huh.
So like for the answer, would it be 0 with the multiplicity of 2?
If they ask you to list, if they just ask you to list the zeros, you can just say 0 and those. Okay, the imaginary ones. But like in your homework, it said, find the zeros. Any 0 that's multiple zeros, list its multiplicity. Then you would list it. Okay? Yeah, Michelle?
It's like 0 has a multiplicity of 2.
Uh-huh.
How does like 2 answers? Or just...
It's just one real 0, because it doesn't hit in a different place, but that's why we tag on the multiplicity part of it, to tell someone it doesn't just cross through 0, but it actually hits 0 and turns around right at that point.
So if an equation has like a degree of 3,
Uh-huh.
so they could be like 2 more solutions?
Yes.
Like the multiplicity.
Mm-hmm. Okay. So there could just be one solution or something, but with multiple multiplicity. Okay? So it's not as important just to be able to list the multiplicity, but more to understand that the multiplicity is going to help you match your total number of solutions with your degree, and that it's going to help you tell how the graph behaves at that 0 on the graph. Okay, like does it cross right through? Does it curve around? That's what the multiplicity is going to help you with more. Okay, so you guys know a bunch of factoring patterns, but there's 2 that you don't know yet, or maybe you do. The difference and the sum of cubes. So you've done difference of squares before. It meant you had 2 perfect squares and the difference between them, and that factored as a plus b and a minus b. Okay. So the sum of cubes means you have a perfect cube and another perfect cube being added together. The difference of cubes would be the same thing, but being subtracted. Okay. And this has a specific factoring pattern. Okay? So I'm going to tell you what the pattern is, and then we'll talk about why it works. I'm going to write it down first, then we'll look for things that can help us remember it. It's not as easy as the difference of squares. So take a minute, write it down, if we want to think about how we end up with the cubes, sorry, let me. If we want to end up with a cubed, say, minus b cubed, there's a lot more powers here than a square, so there's going to be more middle terms, okay? If all the rest of the stuff in the middle canceled out. Now, the last one, let me remind you, was a squared to b squared, and then in the middle terms they had an a and a b and another a and a b that canceled each other out, right? Okay, that's because a started with a power of 2, so then there had to be terms with a with a power of 1 that would cancel each other out, and then the power of a disappeared. Kind of how we write our polynomials from highest degree to lowest degree. B kind of goes in the opposite order. This term has no b's, but we want to work our way up to a term that has b to the power of 2. So what's between 0 and 2 is a power of 1. So b has to exist with a power of 1, but it must have been canceled out, so that's how we know those two terms are there. So here, if we have to make it from a power of 3 down to a power of nothing, there has to be a term where a has a power of 2, and then b has to work from nothing up to 3, so with that, b should have a power of 1. But I need 2 of them because I need them to cancel each other out because I know they're not supposed to end up there in the end. Okay? So a goes from third power to second power to first power. So if a is to the first power, and b's gone from no power to first power to the second power. So we would need a to the first with b to the second, again, canceling each other out, so I need 2 of them. And then a would go down to no power, and b would make its way up to the third power. And I'm not going to touch those ones because those ones were supposed to be what's left. So I put in this stuff here. That would be the stuff that would be in between those if there were terms. I know that they disappear, so I know that they cancel out. Okay? Now let's look at a factoring thing we know how to do, which is factoring by grouping. So if we look at this group here, what do they have in common? A squared. And if I factor that out, I'm left with b. Okay? Next group. What do they have in common? AB. And if I'm trying to factor by grouping, normally we try, if the first term is negative, to take out the negative. For 2 reasons, we usually don't leave a negative coefficient with x. And if we're trying to factor by grouping, we're trying to get this greatest common factor attached to a binomial that looks the same as this one, right? So if I want positive a as my first term right here, that actually works as long as that's a minus right there that I factor out. So then that would give me the minus a squared b, and then if I put right here plus b, no, sorry, minus b, is that right? If I leave it out of what I factored, then the a is going to be negative. Let's see if we can do this. Is that fine? I think I want to reorder my stuff. I'm going to cheat, okay? I'm going to go back here and make this one the negative and this one the positive. You guys know why I just did that? Because I don't like this, right? I don't like that this worked out to be a minus b because I want it to match this one. I just changed the order. I can write them in whatever order I want, true? 3 plus 5 is the same thing as 5 plus 3. And I want these groups to match, and right now they wouldn't match. But if I make this a minus, now I can make this a plus, and now these match. So that's better for me, okay? All right, now I'm going to move on to the last 2 terms. What do they have in common? B squared. And then if I take that out, I have the same problem I had before. Darn it. Okay. All right, let's see. All right, so how did I want to describe this? A squared. Oh, because I want that to be plus. Pause. All right. Not wrong, but just I think this order is going to help me better. So let me look again. Helen?
So if you're doing differently,
Uh-huh.
shouldn't your term be a minus instead of a plus?
Yeah. So I reordered, okay? So all I did was reorder because it didn't work out how I wanted it to do, right?
Are we going to have to redo?
So, no, I'm just showing you why they work. So you should, when is the case when you reorder? If you tried factoring by grouping and you think that it works, and then you try it like I did, right? I was really close, right? I had things I wanted right here. They both had an A and a B, but it wasn't quite matching up sign-wise. So I still think it can factor by grouping, but I don't like how these signs came out. So what I tried to do was reorder my terms in a way that I might get the signs that I want. Okay? You should be able to do that with something like x to the third plus 3x squared plus x plus 3 or something like that. When you guys factor by grouping, if it didn't work out how you wanted to, you should be able to switch middle terms and make it work out. Notice I didn't change the end term and the beginning term because that's where I wanted those terms to end up being. All I did was switch around some stuff in the middle, but it all works out still to cancel out. Okay? So now let's try again. So when I factor out of here, if I factor out a squared, I'm left with a minus b. And then out of here, if I factor out ab, I'm left with a minus b. And then out of here, if I factor out b squared, I'm left with a minus b. Okay? Better, right? Better. Now, what's the common factor that all three of my terms have in common? A minus b. When I factor a minus b out of this first term, what's left of it? So this was factored out. What's left is a squared. And then out of the second term, if this is factored out, what's left is ab. And if this is factored out, what's left is b squared. Okay? So first of all, it works. Okay? Do you have to remember this whole thing? No. You have to remember the pattern, but inquiring minds like Matt over here were a little bit skeptical of how it worked, so I wanted to make sure that you knew it works. Okay? Julia and then Matt's question.
In your equation that you had before, there was no square. Like in your equation that you wrote.
This one at the end?
Yeah.
Oh, it should have a squared.
Okay. Because when you wrote it.
Sorry, let me go back a couple pages then and make sure.
Oh.
Is that okay? Okay. No, that's important. I'm glad you brought it to my attention because if it wasn't there, I would have wanted to fix it. Yes, Matt.
Okay, but I still don't get it because isn't like a cubed minus b cubed the same as a minus b cubed?
No. Okay, so really good question. Is a cubed minus b cubed the same thing as a minus b cubed? No. So let's think about this as being x minus 1, right? If I take x minus 1 and cube it, that's x minus 1 times x minus 1 times x minus 1. It's going to be a little bit of a headache, right? Because x minus 1 times x minus 1 times x minus 1. That's not just going to be x cubed minus 1. Because this part right here, when I multiply it together, is going to be x squared minus 2x plus 1. Now when I multiply that times x minus 1, I'm going to get x cubed minus 2x squared plus x minus x squared plus 2x minus 1. These don't cancel out. So I have x cubed minus 3x squared plus 3x minus 1. So x minus 1 cubed is this. Okay? So just like x squared minus 4 is not x minus 2 times x minus 2. It's x minus 2 times x plus 2, and it's a little easier for us to understand because there's a lot less stuff going on in the middle. Okay? So
then, but how do you use this then?
let's see. All right, so his question is, how do we use this? All right, so let's say we had an equation like this. That's okay, thank you. And we have 2x cubed equals negative 54. Okay? Tell me how you would approach this if I just gave this to you right now on a quiz. I never taught it to you. You just had to solve it yourself. What do you think you would do? Eric? Factor out 2. Or divide both sides by 2? Okay. So if we divide both sides by 2, we would get x cubed equals negative 27. What would you guys do next? Claire? Good. You'd find the cube root of negative 27, which is?
3.
Negative 3. Okay? Because negative 3 times negative 3 times negative 3 equals negative 27. And this is the answer you would get, and that would be all. Okay? But what degree is this function? 3. You found one real 0, which means it crosses through the x-axis one time at negative 3. But does this 0 have a multiplicity of 3? In other words, if I do this, so if I do x plus 3 cubed, am I going to get the same function that I had up there? No. I'm going to get a much longer function, right? So this 0 doesn't have multiplicity 3, which means, what do you think is true about the other two zeros of the function that apparently I have no idea about? Yes, they're imaginary. Okay? So, how is that possible? Well, let's view the problem in a different way. Claire?
Why do you have to factor out the rad 27
Mhm.
times rad negative?
No, because this is a cube root, not a square root. A cube root can have a negative, because a negative times a third negative would be negative. Okay? Julia?
Wait, so I know they're imaginary squares, but
Uh-huh.
if you graph it, wouldn't it just be only hit the x-axis once?
Yes, so if you graph it, it's only going to hit the x-axis once, but that doesn't mean it doesn't turn back around. So let me clarify her question. It's important that you guys hear this. Okay, so she asked, doesn't it mean it only hits the x-axis once? Yes. Okay. If it hit the x-axis once with a multiplicity of 3, then when it crossed through here, I would expect this kind of behavior. Okay? But knowing that that 0 does not have a multiplicity of 3, how does it really cross through this? Normal, just like straight through, right? Which means what must be happening? It goes through this like normal, but it's a cubic. How must it look then? But it doesn't have any other zeros. Okay, so it's got to turn around. Does it go back through the x-axis? So then it just turns around somewhere up here. That's why we'd have an imaginary solutions, right? Same reason, when do you have imaginary solutions with a quadratic or a parabola? When the parabola basically looks like this part of the graph, right? And it doesn't cross the x-axis at all. Okay? So you have one real solution. Your other two solutions are imaginary because it isn't going through this with a multiplicity of 3. It's going through with a multiplicity of 1, which means it must have some other turning points, but they don't cross back through the x-axis. Okay? So, what are the imaginary solutions and how do we find them? Not by solving like this. This only gives us the real solution. So I'm going to tell you right now that if you're asked to solve a problem like this, if it says find the real solutions, you did a good job. If it says what are all the real or imaginary solutions of the equation, or it doesn't classify just to find the real solutions, if it doesn't say just to find the real ones, this doesn't cut it. You haven't found all of the possibilities. Okay? So how do you think we can find all the possibilities? Dana. Good. So we can still divide everything by 2 like we did before, or factor out of 2. If we divide everything by 2, we have x cubed plus 27 equals 0. Notice that these are both perfect cubes, right? So that's how you know you're in the category of sum of cubes, because you have a sum between two things that are perfect cubes. So according to the factoring pattern, x cubed is made by taking x and cubing it. Okay, I want to understand what's actually being cubed. 27 is made by cubing what number? 3. So x cubed is a perfect cube of x. 27 is a perfect cube of 3. X and 3 are the things that we're going to use in that factoring pattern, right? Look back at your factoring pattern. So it said when you had like a cubed plus b cubed, it was going to factor as a plus b times a squared minus ab plus b squared. Okay? The a's and the b's in this case are x and 3. Okay? Not 27, because it doesn't say 27 cubed in our problem. It just says 27, which is 3 cubed. So our b is like a 3. So that means this is going to factor as x plus 3. Here's how I personally remember it. I don't know if you're going to like it or not. The first one goes in the first place here, and the last one goes in the last place here, but squared. So this has to be x squared, and over here at the end has to be 9. And the middle term is these two things multiplied together. So 3x. And then your soap, or whatever you guys like, okay? For the signs. So this factor, you set it equal to 0, and what do you get? Negative 3. Not surprising because we already knew if we solved it the other way, we would get negative 3 as a 0. Now this right here, is it factorable? No. Matt brought up earlier what it was missing to be factorable. Him and Alex, he was saying, no, Alex, it should really say 2ab in the middle. It should, right? You kept saying that. Because if it was 2ab in the middle, this would be a perfect square, right? Like if this had said 6x right here in our problem, this would factor really nicely. Well, guess what? It's never 2ab in the middle. So is this ever going to factor? No. How are we going to then find the solutions that are associated with that quadratic? Quadratic formula, completing square, something different like that. Okay? So let me erase some of this and then I'll do the quadratic formula. We got the real solution through this method also. Okay? Yes, Cody.
So how would you do this if like it was a quartic function and like you had gotten like you got into this step and then like you can't use the quadratic function to solve the cubic?
Well, then we'd be kind of stuck. So we're going to look at some calculator tools. There are some quartics that we can solve with these methods and some that we can't. So these methods aren't the end-all, be-all, but they can help us get through more than what we thought before. Okay. Is that right? Somebody checking my arithmetic? 9 minus 36, yeah. Okay. All right, so these are our imaginary or complex solutions. So if we're just trying to graph or something like that, it's nice to know that this real solution exists and to understand it doesn't have multiplicity 3, so there must be a turnaround somewhere else. But if we're trying to find all of the solutions, including the imaginary solutions, meaning they haven't like restricted the directions to the real solution, make sure you do this. This is one of the most common errors. Okay? People will see this, they'll solve it just like this, they'll get negative 3, they'll be done. But if we're looking for every solution, including those imaginary ones, we need to use our factoring pattern, and then we need to solve that quadratic using one of our methods that we know how. Okay? Yes, Monet. So we did do the sum of cubes. So once we divided everything by 2 first, because there was a common factor of 2. So once we had x cubed and 27, x cubed and 27 are both perfect cubes. So we used this factoring pattern to factor it, okay, with x and 3. So our a and b got replaced with x and 3. So that's how we got this right here.
Yeah, but then why did you use factor?
Because this factor gets set equal to 0 and you get x equals negative 3. When you set this factor equal to 0, it doesn't factor further. So how else are you going to solve this factor if it doesn't factor anymore? Quadratic formula or completing the square. Okay? Yeah, Hannah?
Why is it 2 factor?
So you could do this 2 ways. You can divide everything by 2 because we have it set equal to 0, or you could have written this as x cubed plus 27 times 2. And then you could include that 2 as a factor right here. But when you're looking for zeros, in order for 2 times something to equal 0, one of these numbers have to be 0, and I already know for sure that this one is not equal to 0 because it is absolutely equal to 2. I'm not sure what these factors are equal to because they have a place for me to plug in x, so I say I can make this factor equal to 0 when x is equal to negative 3. I can make this factor equal to 0 if I made x equal to either of these imaginary numbers. Okay? So whether you leave it there or divide it out, your answers for your zeros or solutions will still be the same. Okay? Any other questions about that? So a new factoring pattern that you have to learn, right? Okay? So same idea, factoring solves stuff for you, but a new factoring pattern, and because we now have degree 3 or higher, you might not just have to factor once, you then might have to use another method to solve the rest. Okay? This was all of our scratch work. Sorry. All right, so now on the calculator. Okay? So go ahead and take out your calculator. Again, we did a really good job in quadratics. So if you were with us in quadratics and you followed along about everything, how to do on the calculator, which based on the calculator parts of the exams, I would say that most people did, then you know how to find zeros, maximums, and minimums. Like yesterday at the end, I just let you go, right? Like, oh, go find the maximums and minimums. I just made sure you understood the difference between relative maximum and an absolute maximum. So here's the same thing. It's asking us to graph it and then find each real zero to the nearest hundredth and state the relative maximum or minimum. So you're just kind of reviewing what we did last time. So I'm going to write down one of these. I'll do the first one with you guys and then let you do that. So if you were not good at the calculator, now is the time to kind of pay attention because we're going to go back through those keystrokes. So on your calculator, if you're already doing it, you're fine. Go to y equals. Make sure all the plots at the top, plot 1, plot 2, plot 3, all those are turned off so that they don't interfere with you trying to graph this function. Then go ahead and type in the function. So 2x cubed plus 6x squared minus 14x minus 12. Oh, man. Sorry, my calculator doesn't give me a little exponent thing normally, so I don't do that. Thank you for those of you that pointed it out. Okay, so plus, wonder what that graph would have looked like. Okay, I'm going to go to my standard window first. So for those of you that don't know how to get there, I'm going to go zoom 6. I'm going to check out how much of the graph that gives me and then decide what I should do to make it better. So look at my screen. You can see what my graph looks like. Clearly, I don't need to go as far left and right as I currently am, but I need to go further up and down. Oh, is it plus 12? Sorry, I just copied it down off the screen. Yeah, it is. Thank you. Let me go back and fix it. Sorry, I copied it down wrong off the screen. Okay. I need 2 computer screens so I can do this all at once. All right, so now I'll graph it. Okay. So now I see that I need to see further up because I can see that the graph is going up, and then I can see a little dip, so it must continue up. I don't necessarily need to see as far to the left or to the right as I am, but it feels like I need to go much higher up. So I'm going to customize my window myself. So go to Window, and there's no quick solution to this. You can use anything you know about your graph to help you, but you're just going to have to trial and error. Like you guys will ask me, what's the right window for this, Ms. Dahl? And I'll try something, and if it doesn't work, I'll try again. You guys have to do that same thing. Okay? So in my window, I'm going to just go over to like -6 on the x-axis and +6 because I didn't need to go as far left and right, but I need to go up much higher for my y maximum. Did anybody trial and error find a good maximum? Helen? Around 60. Okay, so if I change my maximum to 60, I then might want my scale to be like by 5s or by 10s or something like that. It doesn't matter that much, but it might help. Okay? So now I'm going to go back and graph again. All right, so that's a much nicer view of my graph. Now, to find the zeros on the calculator, are you going to be able to find the imaginary zeros? No. You're only going to be able to find the real zeros. Do you know that there are imaginary zeros for this problem? Yeah, because it's a cubic, so what's the maximum number of zeros? 3. You see one real one. If that one has multiplicity of 3, then that covers it. Otherwise, there must be some imaginary ones if it's just crossing through like normal. So look at the picture. When you see it cross through this 0, it's crossing through like normal. It's not curving like a cubic through there. So this just accounts for one of our zeros, which means there must be a pair of imaginary zeros out there. Okay? And imaginary zeros will always come in pairs. So you'll never have just I as one of your zeros. You'd have to have I and -I. Or 2 plus I and 2 minus I. Does anybody have any idea why they always come in a pair and why they can't just come separate? Cody? Good. If you're getting I, that means you had a negative in the radical in the quadratic formula, right? And what comes right before the radical in the quadratic formula? Plus or minus. So you're never just going to get the I part with just the plus or just the minus. You're always going to get it with both. So they always come in pairs. So I would expect one real zero with 2 imaginary zeros. And on the calculator, I'm only going to find my real zero. Okay? And the way we're going to find our zero is we're going to go second, trace, which is calculate. And in this case, we're looking to calculate a 0, which is choice 2. remember when it asks for left bound, you want to go to your 0. It's going to take me a while, sorry. And my words are right over where I need to do this in my window, but I can do a pretty good job. If I can't see where my cursor is, notice that right now it's telling you what numbers you're at. I'm at the point negative 4.7, 1.2. Am I to the left or the right of my 0 right now? The right, because the way my graph travels, the left part of the graph would be below the 0, and the right part would be above the 0. But the y-coordinate right now of the point I'm at tells me I'm above the 0. So I better not use this as my left bound, or the calculator will probably give me an error. I need to keep going left till I'm below the axis. So I'm going to go left again, see if that's enough. It is. So I'm going to press enter. And then when it says right bound, I'm going to go back to where I was above the point, and that's just because of the way the direction the graph grows. Press enter, and then say yes, yes. And so my 0 is at negative 4.7427. Okay? And then we talked about relative maximums and minimums yesterday. Does everybody feel comfortable with finding a maximum or a minimum? Hannah? For this that we just did? So the right bound, so because the graph is going like this, right here, okay, here's what you're trying to calculate. To the right of that is this way, which in our graph, points that are to the right of it are below it. So when you pick the right bound, your cursor needs to be somewhere below the graph. And then when you pick the left bound, left here would be as our graph travels up, it goes to the, or sorry, other way. Yeah. Left was below, and then as we travel up to the right. So then that would be our right bound. Okay? Yeah, anyway. Okay. All right, now I'm going to let you guys go back and finish relative, maximum, and zeros because you guys know how to do the calculator work for that. Again, we did it in quadratics to make it easier for us later on. And we're going to discuss this last problem, which is a word problem. And I really didn't type it all together, but it makes it appear as though I did. So, sorry. There we go. All right. So, the word problem says, what are 3 consecutive even integers whose product is 4 times their sum? Okay, mouthful, right? Like a lot of math vocabulary there. Okay? So, first of all, let's talk about consecutive even integers and how we would represent them. What do you know about consecutive even integers? Eric? They increase by 2. So one way that we represent integers in math, you could use x or you could use n. A lot of times people use n. But we'll use x because it will help relate to what we've been doing here. If x is your first integer, okay, I know it has to be even. Yes, so x is my first integer. What would be the next consecutive even integer? Helen? And what would be the next consecutive even integer? Good. So here are 3 consecutive even integers. Okay. Then what we're going to do is try and set up an equation based on what the problem said. So the problem said, what are 3 consecutive even integers whose product is 4 times their sum? So what does that mean? What am I doing? Julia? Okay, so she said when you multiply them, the number that you get is 4 times more than when you add them together. Is everybody okay with that description of what's going on? So now I'm going to take that and say, okay, when I multiply them, the answer I get, or the number I get, or it is equal to, okay, 4 times more than when I add them together. Is that okay? So it looks a little bit horrific, okay? But what are we going to get on the left side? A cubic, okay? And you might, like the first inclination is like, oh, I don't want to multiply it out, like it's already nice and factored. But those factors don't do us any good unless it's set equal to 0. So we have to multiply it out to get all the combined terms together on a side, and then we'll try and see if we can factor it again. So here, when we multiply this together, we get x squared plus 6x plus 8. We're going to multiply that all by x. Okay, so we have x cubed plus 6x squared plus 8x. On the other side, okay, first of all, the sum of these integers is going to be 3x plus 6. Okay? Then that's getting multiplied by the 4, so I'm going to have 12x plus 24. Okay? And then what I'm going to do is move everything to the same side. Well, I said 24. Well, this will be minus 4x when we move over the 12 and minus 24. And then what would we do to try and go about solving this? Okay, we could graph it and we could find the zeros that way. What if we can't use our calculator? Factor. How could we try to factor this? Okay, so we can take out common factors first. Now, there's not one common factor for the entire equation, but if we group, okay, like we saw earlier, we can take x squared out of here. And out of the next two terms, we could take out negative 4, giving us factors of x squared minus 4 and x plus 6. And then we could solve it from there. Sorry, you guys, but we didn't get to stand. Okay, but are you okay with solving it from here? So you would get 2, negative 2, and negative 6. Okay? Now you'd have to check if all those possibilities of x actually work as the even integers that would work out. Now remember, they're just giving you solutions for this. Okay? So the answer is either 2, 4, and 6, or negative 2, 0, and 2, okay, etc. All right?